Coastal Maine is a unique place in North America, lying on the very edge of the continent. Its landscape evolution mirrors that of the rest of the continent in the way that the continent was assembled. In recent years, an understanding of the complex evolution of the northeast coast of North America has been influenced by an understanding of plate tectonics. We've learned that microcontinents and island arc systems, much like those of modern-day Japan and Taiwan, have been added to our ancestral home sequentially through time. These collisions, as well as continent-to-continent collisions, have grown the continent by adding new pieces. Indeed, this is the story of much of the landscape of the world, perhaps adding to the unique character of our planet is the only one that we know of that sustains life with oceans of water and a thin, oxygen-rich atmosphere that we call home. Let us start by looking at the prominent roadside cliff at Camden, Maine. Climbers on Broadway at, at Barrett's Cove Cliff face a red-brown rock containing very small red garnets and white muscovite and black biotite micas. There are white quartz lenses throughout. In the photo, climbers stand below Upper Charlotte's Crack. You can see some of the quartz lenses to the left of Charlotte's Crack. Kenton Rock has beginnings a long time ago, somewhere in the range of 541 to 485 million years ago, and they have been transported, altered by heat and pressure 430 million years ago, and were once part of a mountain range that rivaled the Himalayas. It is now, of course, worn down to its roots and sits near sea level. Camden area and its rocks fit into the regional landscape of Maine as part of the coastal Maine volcanic belt. This belt stretches along the entire coast and includes intrusive igneous rocks such as the Acadian granite and the Lucerne granite of Clifton, Maine, as well as volcanic rocks. Importantly, there are also rocks similar to those in Camden that are now metamorphic rocks that have been converted by heat and pressure from earlier rocks. Geologically, coastal Maine is separated from central Maine by the Norumbega Fault. This is shown on the map as a black line running from southwestern Maine towards the northeast. This fault is the largest in New England and plays an important part in the origin of the rocks of coastal Maine. The fault, no longer active, has a complex slip component with prominent slip showing the east side slipping northward, forming an analogy with modern-day San Andreas Fault in California. Mount Desert Island is shown in the color blue by an arrow, as is Clifton, Maine, where Big Chick is located in the Lucerne batholith, as these are igneous batholiths. Camden sits southward on the coast about where the letter E is located in the word Camden and is shown in pinks and browns, as these are metamorphic rocks converted by heat and pressure from older rocks. The granite at Acadia is dated to 420 million years, whereas that of Clifton is dated to 388 million years. As the origins of granite is melting at depth within the earth, this perhaps shows that melting progressed from east to west. Camden rocks are older than either of these two igneous intrusions. Maine's coastal rocks form south of the equator. To understand how they were transported northward and came to be on coastal North America, it's important to look at plate tectonics. Lithospheric plates are plates of rock that include both surface rocks and extend downward beneath the surface for many miles. They sit on the asthenosphere, a layer within the upper mantle near melting that provides a sliding surface for the rigid plates above to slide about. The present-day arrangement of lithospheric plates is shown on this map. There are seven major plates, separated either by mid-ocean ridges where new magma comes to the surface, and then a cooling plate moves away from the ridge. Mid-ocean ridges, such as the Mid-Pacific Ridge of the smaller Nazca Plate off of South America, show red arrows pointing away from the ridge. These ridges are some of the highest places on the planet, but we don't see them as they are covered by water. New ocean floor is formed at the ridge and pushes the plate towards South America. As the plate moves, it cools and sinks, and gravity pulls it beneath South America. As the plate is subducted, it partially melts. Partial melting occurs in the descending plate, and the magma form then rises as it is of a lighter density than the continental rock around and above it. When it reaches the surface, it forms a chain of mountains inland from the coast that is the Andes Mountains. Plate tectonics, taken to its logical limit, implies that as one lithospheric plate moves away from another, it might crash into another plate coming from another direction. Research shows that this has indeed happened more often than not, and eventually all the landmasses of Earth come together into one big landmass, or supercontinent. Research recognizes three of these supercontinents that are definite, going back more than a billion years, with the possibility of more supercontinents further back in time. Supercontinents form, split up into large chunks, and separate into smaller chunks and slivers of land. Today, our largest landmass is that of the combined Africa, Europe, and Asia, making up about 57% of land masses. The three definite supercontinents are those of Columbia, Rodinia, and Pangaea, shown in the illustration. The oldest of the definite supercontinents is Columbia, named because basaltic lava flows in eastern India are connected to those of the Columbia Plateau in Washington state. These basaltic outflows are some of the largest that has occurred in Earth history. At 1 billion years, the supercontinent Rodinia formed. It later broke up to produce both southern as well as northern plates and landmasses. It is possible that Camden area rocks originated here, although one of the pieces formed from the breakup is the more likely place of origin. From this breakup, the largest southern piece was Gondwana, created about 530 million years ago. Later continents again came together to form the supercontinent Pangaea when Gondwana moved northward to collide with northern landmasses. Gondwana plays an important part in our story since this landmass is where Camden, Maine area rocks most likely came from. Today's present-day Atlantic Ocean began to form when Pangaea broke up, somewhere on the order of 170 million years ago. With this quick rundown of the movement of continents through time, we will focus on Gondwana since that is where Camden Age rocks were created, somewhere around 500 million years ago. Gondwana became famous when Alfred Wegener proposed the concept of continental drift in a 1912 paper, where he noted that South America and Africa would fit nicely together if we just slid them together on the map. Later researchers discovered plants and animals in the southern continents that also fit together like a jigsaw puzzle. Almost all these animals and plants could not have swum across or floated across modern oceans. So they also propose that these land masses fit together at one time. Most scientists, however, called the early observation circumstantial. Critics of the concept of continental drift could not envision continents sliding across a solid Earth as it was believed to be at the time. There was no smoking gun to prove the concept. In the 1950s, focus of scientific research turned to exploring the seafloor, about which little was known. The first exploration of the ocean floor was a 3-year-long 1898 British expedition by the HMS Challenger. Before the Challenger expedition, more was known about the surface of Mars than that of the ocean. People at the time believed that the ocean got both deeper as you moved away from land and older. However, the Challenger expedition, taking depth soundings with a long rope, mapped ocean depths worldwide and discovered that the ocean was shallower in the middle than closer to the edge. At the start of the 1950s, the floor of the ocean remained largely unknown. During the 1950s, systematic ocean survey data was sent to a cartographer at the Lamont Doherty Laboratory in New York, who, while charting this data on a map, discovered that not only was there a mid-ocean chain of mountains, but in the middle of the chain was a rift valley. Furthermore, this rift valley was where mid-ocean earthquakes were located and where new lavas flowed. In addition to the new lava information, other information emerged showing the age of the ocean rocks were youngest at these mountains and got older as you moved towards land. Additional discoveries soon followed that allowed understanding of seafloor spreading. A second cornerstone of plate tectonics is the existence of the asthenosphere. A layer much like the asthenosphere was first proposed in a theoretical paper in 1914 to explain the established observation that mountains seemed to get higher even as they were being eroded. But it wasn't until the 1960s that geophysical surveys established the separation of the lithosphere and the asthenosphere in both their existence and extent. By this time, the concept of seafloor spreading, the existence of the asthenosphere, and plate tectonics was established. As a result, it was a long scientific journey from Wagner's initial crude proposal to a clear and acceptable model of the nature of Earth's outer shell and the mechanisms that is modern plate tectonics. A look at ancestral North America shows that it too was formed by the assemblages of microcontinents and formed by mountain building in ancient times. Ancestral North America consists of a core of very old rocks that has been in existence for several billion years. This core is called the craton, meaning that it has been stable for a very long time. The right-hand illustration shows that the craton is centered around the Superior province and its rocks in Canada, with belts of rocks added to the sides during the creation of supercontinents and assemblage of small pieces. These pieces in turn were derived from earlier continental collision. Maine itself consists of younger belts of rocks created from collisions with island systems and microcontinents, with the youngest of these making up central Maine west of the Norumbega Fault, and the coastal volcanic belt, which is composed of Avalonia rocks and intrusions. Since modern-day Maine rocks are highly deformed and metamorphosed, new information about the sequence of events is both complicated to discover and newly emerging. A feature of our planet is that continents form, break apart, a move with new oceans forming. We can find similar situations of continental splitting today in the East African Rift Valley and Red Sea and Gulf of Aden. The later breakup of Gondwana happened in a series of rifting that took place over a period of millions of years, with collisions of microcontinents and island arc systems with Laurentia from approximately 420 million years before present to 290 million years before present. Island arc systems were similar to those of the Japanese and Taiwan archipelagos today. These microcontinents and island arcs collided with Laurentia at different times, with ocean basins being subducted entirely while new oceans formed. The microcontinent most related to the development of Maine's coastal rock is that of Avalonia. Avalonia was large enough that various parts of it were incorporated into southwestern Great Britain, Southern Ireland, Newfoundland, Rhode Island, and elsewhere, as well as the New England coast. In all, 9 current countries contain pieces of Avalonia. Avalonia moved from Gondwana across the ocean Iahitis. Since this ocean was ancestral to the modern-day Atlantic, it was named for the father of Atlas, for whom the Atlantic is named. If you look closely at the microcontinent Avalonia in this diagram, you will see not only the future coastal Maine, but also outlined in red, southeast England, southern Ireland, and a bit of continental Europe. Another large piece of the supercontinent of Gondwana, named Baltica, was incorporated as modern-day Scandinavian countries and a bit of European Russia. Gondwana later collided with the combined Laurentia and Asia called Laurasia, so the northern east coast of U.S. rocks are related to those of northern Europe coastal rocks. The landscape of Laurentia, after Avalonia impacted, formed a mountain range on the east coast of Laurentia with a shallow sea forming inland in the Appalachian Basin. This basin collected sediments worn off from mountains, that is, the Catskill Delta. Today, this is represented by the Catskill Mountains. The Catskill rocks are formed of sand and silt, oxidized red in color, indicating deposition under the open air. These sediments show typical stream deposition features. An insert photograph shows the erosional setting of the Catskill Delta and that of Catskill Falls, New York. The most inland Gondwana terrain in Maine is the Gander terrain. The Gander terrain of central Maine, west of the Norumbega Fault, broke off from Gondwana along with Avalonia and others and collided with Laurentia about 450 to 420 million years before present. Waterville, Orono, and generally central Maine northward are underlain by this terrain with younger sediments deposited on top. The Iahitis closed with the Norumbega Fault, in this model being related to a subduction. To the east of Avalonia, between Avalonia and Gondwana, a new ocean formed called the Reek Ocean. This in turn contained small island arcs. Subduction zones that form as part of this process are shown in the lower cross-section by black lines. In this process of accretion, these island arc systems and microcontinents, the Iahitis closed and was either subducted or left scattered traces on land. To the east of Avalonia, between Avalonia and Gondwana, a new ocean formed called the Reek Ocean. This in turn was subsumed when Gondwana accreted to Laurentia, completing the cycle. Other terrains had broken from Gondwana and collided with Laurentia elsewhere. The Carolina terrane accreted to southern Gondwana between Georgia and Virginia, and in southern Nova Scotia, the Maguma terrane accreted to the Avalon terrane. The map is above is a 2015 interpretation, does not appear to represent more recent discoveries, including that the chain of lakes Massif could be as much as a billion years old. Continental collisions involve huge forces. These forces may involve melting at depth, producing batholiths that are large bodies of igneous rock, mostly granite. Most granite batholiths form deep in the earth and can contain a limited volume of gases. As a result, they have thousands of years for large crystals to grow during the cooling process. Only after thousands or tens of thousands of years of erosion of the overlying rocks are these batholiths exposed at the surface. This is the case for the Lucerne granites and the Mount Waldo granite, as well as most granites in Maine. Some batholiths form under the surface containing potentially explosive gases, so that overlying roof rocks cannot support the liquid below and collapse. Collapsed structures are called calderas. The Acadian granite at Mount Cadillac, as well as Crater Lake in Oregon, both formed calderas. Broken rocks in the collapse area are cratered around the sides of the descending roof rock. You can see the shatter zone of rocks around the edge of the Cadillac granite on the edge of the Sea Anemone parking lot in Acadia National Park, or with a little more effort at Little Hunters Beach. Many of the roof rocks are partially assimilated into the granite, whereas others remain sharp and obviously composed of broken pieces. On the land surface, can find volcanic ash and flows. In each case, the liquid batholith was intruded up to 7 miles beneath the surface that existed at the time. That these batholiths are exposed today shows that much erosion has subsequently taken place. The Acadian granite of Mount Desert Island has an age of 420 million years. Melting and presumably collision forces moved inland to the Lucerne batholith later at 388 million years, and the nearby Mount Waldo batholith in Frankfort, Maine at 371 million years. The climb in the photo is Birch 8, currently with a 5.9 start, but back in the day a birch tree growing in what is now the 5.9 crack prevented free climbing this. When the birch tree was alive, you could bend the birch tree over and stand on it to avoid this move, so that the whole climb was simply a stiff 5.8, as the entire climb requires a sustained effort. The Acadian granites were intruded into the pre-existing rocks, which collapsed around the edges, forming a zone of shattered rocks. Perhaps Crater Lake in Oregon can provide a model of what the area might have originally looked like. Crater Lake sits in a collapsed structure where molten rocks were intruded under the overlying existing rocks. There was not enough structural strength in these overlying rocks to span the molten rock, and the roof collapsed. On the surface in Maine, there would have been volcanic rocks, as at Crater Lake, but any melt that cooled at depth would have large crystals, such as we see in the Acadian granite. What we see today in Acadia is the roots of the crater, after many miles of overlying rocks, was eroded off. This granite is coarse-grained and forms the precipice and sea cliffs. A medium-grain granite forms on much of the western part of Mount Desert. Clifton, Maine hosts a number of cliffs including Parks Pond Bluff, Fletcher Bluff, and Big Chick, among others. These all lie within the Lucerne granite that forms one of the larger granite bodies in Maine. This granite is very coarse-grained, grayish-white granite containing two types of feldspar that tend to weather out in relief. So much so that climbing on the granite depends on protruding feldspar crystals for foot and handholds. A photo showing feldspar quartz crystals is in the lower left, while the cliffs of Big Cheek are shown in a photo taken from the highway. A map of the Lucerne granite is to the right, with the batholith occupying the triangular shaped white area in the graphic. The Lucerne granite sits inland from the coast and is younger granite than that of the Acadia, perhaps indicating melting moved inland through time. The Norumbega Fault, noted by an arrow in the diagram, separates central Maine and its rocks from coastal Maine rocks and Avalon. Big Chick is a popular climbing area in the Lucerne batholith. Climbing consists largely of standing on feldspar crystals, one of the ingredients of granite, that have weathered in relief while gripping the same crystals with your hands. It calls for heady climbing with trust in your feet. This is Weekend Warrior of 5'8". We arrive at Camden, Maine, where Professor Philip Osberg and Professor Berry created a map of the rocks over many field seasons of work. On the map, different units of rock are shown as different colors. The mapping cross-sections that follow show that these are layered rocks that, as we will discover, are originally marine sands and muds. Barrett's Cove Rock is at the top of the map, sitting above the cove of Lake McGunnicook, and is shown by an arrow. Mount McGunnicook cliff-forming rock is orange-colored and is labeled EMCQ, being a calcium silicate quartzite member. Most likely this unit originally was a sandstone with calcium and other chemical impurities. This unit forms a prominent cliff up to 30 meters or 100 feet high above the west side of Mount McGunnicook above the tableland. A more recently intruded granite is found along the shore of the cove in the southern end of Fernall's Neck. This granite is not as resistant to weathering as the metamorphic rocks of the climbing area and is weathered into a low area along the lake. Dr. Osberg and Berry drew cross-sections of the Camden rocks along lines shown in the insert map. The top cross-section, AA prime, shows a reconstruction with dashed lines extending above the current ground surface. These are overturned and broken off fold structures that we will explore in a minute. BB prime goes across Mount McGunnicook and shows a fault structure on the left that is the McGunnicook River Fault. This fault, or break in the crust, resulted from regional tension or pulling apart of the rocks. It most likely occurred long after Avalonia collided with ancestral North America and may even have occurred when the Atlantic Basin began opening much later. The lower two cross-sections have dark lines representing thrust faults. Thrust faults, in contrast to normal faults, result from compression when pressure from the side pushes against the rocks. These faults most likely occurred when Avalonia crashed into central Maine. Thrusting here is from the ocean landward as Avalonia crashed into ancestral North America. Folding of large bodies of rock can occur when they are buried under overlying rocks with slow forces pushing them from the side. Shown on the screen is a dramatic example of folding in the Alps, where an S-shaped fold resulted. Here we can imagine pressure from the right pushing the rocks over to the left. In the Alps, these folds were broken off from their roots, and the whole block of rock was moved along for many miles from where the folding originated. Now consider what this might look like if it were eroded to a more or less sea level plain similar to the Camden area. A lot of field work and interpretation would be required to reconstruct the original structure. Here are similar small-scale folds show pressure from the left pushing the rock to the right, with one of the fold structures broken off and pushed and thrust a short way to the right. The double-headed arrow shows the thrust fault, and the single-headed arrow indicates relative movement on either side of the thrust. You can recreate this type structure by taking a sheet of paper and pushing it from the left while holding the right side down. Folds will form and then overturn to the right, and eventually with enough pressure, the paper will tear and you will thrust the left-hand folds over the right-hand folds. Mountain ridges have thrust on a huge scale. Perhaps the most famous mountain in the world is the Matterhorn, with its glacially carved sides rising to a pyramid-shaped peak. Rocks of the Matterhorn were originally African in origin, but were thrust into its current location over younger rocks that were formerly part of the ocean floor as part of the development of the Alps. Similar long-distance thrusts are found in the Rocky Mountains and even along Lake Champlain in Vermont. Rocks in Camden today are mostly metamorphic, having been altered by heat and pressure during the culmination of the mountain building process along the coast. Prominent rock types are the quartzitic conglomerates of Mount Batty, the quartzites of Mount McGonagall, and the schist of Barrett Cove Cliff. But what might have they looked like originally? In the Camden area, Mount Batty provides important clues as to the origin of the rocks in Camden before they were metamorphosed that changed their character. Near and on the summit of Mount Batty is a quartzite conglomerate made up of quartz pebbles. These are of good size without much else in the rock. Today we can find unaltered quartz pebble sediments in high-energy beaches, marine channels, or basins. What is important here is that wave action and transportation broke down and removed other types of minerals and materials such as clay and other particles of a smaller size. This is undoubtedly the origin of Mount Batty rocks. If you descend from the summit of Mount Batty and cross the outer road headed to Mount McGonagall, you will find small outcrops of rock along the trail that show clear-cut water lane current features. One such outcrop shows bedding with quartzite in the upper part, as shown on the slide, and finer layered sand in the lower part. Within the sand, parallel lines show bedding planes, and near the top of this layer, these have been washed away with new layers of sand deposited at an angle to the lower layers. These are called cross laminations. This type of cross lamination is common to water-lane sediments. It is a strong clue that the quartzitic pebble conglomerate of Mount Batty's summit, the quartzites of Mount McGonagall, and even the schist of Barrett Cove Cliff were originally water-laden sands and muds before later being transformed in the mountain building process. Deciphering how the schist of Barrett's Cove Cliff came into being takes a bit more detective work. Research has shown that this type of rock originates from sedimentary mud or mudstone that is commonly found in marine environments. If you think of a mud as a chemical soup, compounds in the mudstone include aluminum oxide, sodium chloride, calcium oxide, iron oxide, silicon oxide, and so on. With heat and pressure, the old minerals that were stable in the mud are no longer stable and new more minerals form. Importantly for schist formation, platy minerals such as micas form, and with directed pressure, these grow and lead to a type of layering called foliation. The Bears Cove schist contains both black and white micas, called biotite and muscovite respectively, as well as very small garnets and other minerals. Looking at the cliff again, you can see white quartz layers on the wall above Broadway, prominently to the left of Upper Charlotte's Crack, as well as the wall to the right. These may well have been original sand lenses within the mudstone. Alternatively, metamorphic process could also have given rise to these layers. We've now answered the question of where did Camden rocks originate? How did they get to their current location? And their marine origin. What remains, however, is to explain how the cliffs formed. We will start by looking at the landscape just before the last glaciation and what effect this last glaciation had on the area and its rocks. What did the landscape look like before glaciation? Before glaciation, Mount Batty was still there, Mount McGunnicook was still there, and so on. However, any rock climbers in existence at the time would not have come to New England to find cliffs. They would have to go somewhere south of the glacial limit, where geology was kind and presented upturned rocks such as those at Seneca Rock, or maybe to an erosional remnant such as Stone Mountain, Georgia, to find rock to climb. Yosemite would have been a boring place for rock climbers, but hikers would have still enjoyed it, and Half Dome at the time would have been Full Dome. If you stood on top of Mount McGunnicook, it might have been a few feet higher, but no matter what direction you looked at, it would have all been equally rounded. There were no cliffs. Let us look at cliff formation. During the last few million years of Earth history, the northern portions of Earth were glaciated by continental-sized ice sheets. These ice sheets had the effect of accentuating landforms that had been created during plate tectonic processes discussed earlier. We started with the Laurentine ice sheet that covered North America a couple of million years ago, extending down into New England, New York, Ohio, Wisconsin, and so on. There were over 3 dozen glacial cycles of advances and recessions over the last 3 million years, with the configuration of the ice sheet on the map being the most recent recession from 18,000 to 14,000 years ago. The arrow on the right side of the diagram shows the northwest to southeast movement direction of the ice in Maine. In New Hampshire, ice movement direction is more north to south, and in New York from northeast to southwest, indicating an ice center in Labrador. Other movement directions are shown by lines within the ice sheet, related to different ice centers. This ice sheet played an important part in creating the cliffs at Camden and elsewhere. This is a look at Daft Dawn out in Tuolumne Meadows. Daft Dome is a great example of what happens to a rounded hill that is eroded by a glacier. The arrow in the upper left photo shows glacial movement direction. On the right side is an eroded slope called the Stowe side, and to the left is the lee side with the cliff. The lower diagram shows glacial coring or plucking on the lee side. Hill slopes in New England have this asymmetrical shape. In Maine, the Stowe side is generally on the north-northwest, and the lee side is on the south-southeast side. Looking at the lee side of Half Dome, if you look closely, you can see climbers on West Crack's third pitch with an arrow pointing to them. This is the large diagram or photograph on the right. I did the first pitch of this climb with Ben Townsend, but since it was near dark, we had to descend. Later, I returned with a former Camden climber who was at one time a student at Unity College, and we did the entire climb. I highly recommended it to you. There's one 5-9 face move at the start protected by a bolt, with the rest being a more mellow 5-8. This shows more detail of how a moving glacier can create a cliff on a previously rounded hill. Within the rock, there are vertical lines representing weaknesses or fractures in the rock. At the base of the glacier, there's a lot of pressure and a basal melting of the ice occurs. This water seeps down into the rock along the fractures. The water freezes in the fracture, expands the rock, helping to break off blocks of rock. These blocks in turn freeze to the moving ice, so that as the glacier moves along, the rock is pulled off and quarried. This is also called plucking and carries the rock away. This is most effective as the ice moves away from the hill and a cliff results. Note also that the moving ice contains a load of rocks frozen into the base of the glacier. This is called the basal load. As the basal load rocks are carried along with the ice, they gouge and scrape the underlying rock. This often produces grooves in the bedrock that are deepened depending on the hardness of the bedrock. The entire hill, including the Stowe side as well as the lee side, suffer erosion. Standing on Mount McGunnicook's Ocean Lookout, shown in the large photograph on the right, focus on the rock in the foreground. It shows the hard quartzite of Ocean Lookout. These hard quartzites have been grooved by rocks that are carried at the base of the moving ice sheet and act as an abrasive on the landscape. These grooves appear as fine parallel lines that you need to look closely at to see. An arrow is placed parallel to the fine grooves. For contrast, in Westbrook, Maine, where the landscape rocks are softer, grooves can be deep and are readily apparent. Now let us look on a wider scale, shown by a topographical map of the Camden Hills. The continental ice sheet had a great effect on the final appearance of the landscape in Maine. 16,000 years ago, Maine was covered by ice. 13,000 years ago, the ice was gone, and the landscape looked much as it looks today. As the ice passed over an existing hill, such as Mount McGunnicook, it interacted with the rock weakness direction to quarry the hill as it moved along. As a result, a cliff resulted. A topographical map of the cliffs at Camden show the cliffs and an arrow showing the north-northwest to south-southeast movement direction of the ice across them. The final orientation of the cliffs then is related to rock weakness as well as glacial movement direction. In Camden's case, this produces a cliff on the southwest side of the hill running north-northwest to south-southeast. What happened to the material removed from the cliffs? Some of it was not taken very far. Before Barrett's Cove Cliff, there were blocks of rock plucked from the cliff and dropped from the ice as it melted. Climbers have created a few boulder problems on these. Other blocks, without doubt, were carried out to sea and dropped out in the Gulf of Maine. The best known plucked rock in Maine is Bubble Rock, sitting on the bubbles in Acadian National Park. This is a block of light-colored granite that sits on the Acadian granite that weathers a rusty color, preventing, presenting a photographic color contrast. Bubble rock is Lucerne granite carried by glaciers for about 35 miles from its origin somewhere in the Lucerne batholith near Big Chick. If you go to Big Chick and stand on top, look towards Mount Desert Island and imagine the journey that the bubble rock made. In conclusion, Canyon Rocks and its cliff had a long odyssey, starting the sediments south of the equator, splitting off from Gondwana, traveling across the Iapetus Ocean, crashing into ancestral North America, creating folds and thrust faults to create a great mountain range that eventually wore down to sea level, was overrun by glacial ice and quarried as the ice passed over. Today it sits in a serene environment next to the sea, overlooking the landscape. You have to love it, enjoy it, and experience it. Thanks to everyone for listening to this trip through time. I enjoyed learning things I never knew or paid attention to when I was focused on climbing. Hopefully you have learned a bit and enjoyed it a bit as well. Till next time, thank you very much for listening. Bye for now.